Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of our Tactica Tutorialis science lesson videos, and today is going to be a GCSE physics topic looking at nuclear fission. We've done some nuclear physics in this series already, and you can check the link in the description for the playlist. But today we're going to look at probably the most famous aspect of nuclear physics, that being when atoms break down and fissile material goes off, and this is in the end what created the nuclear bomb. But we're not going to look at it in the context of nuclear bombs today. We're going to be looking at it in terms of nuclear reactors. So the main process of what we're going to do today is we're going to look at what fission is and what happens during fission. We're going to explore the concept of a chain reaction, and we're then going to explore in detail how a nuclear fission reactor actually functions and how we avoid consequences that we've seen at some reactors around the world throughout history. And we will talk a little bit about that toward the end, though that does go slightly beyond the actual specification, so I will save it either for the end or for a bonus segment if I want to put that in the description. This is going to be a dense lesson. There's nothing I can do about that. Fission is a very important topic, and it's also a topic with a lot of moving parts. So if you want to get your head around some of the nuclear notation, such as the atomic notation that we've used before, I thoroughly recommend you check the description and have a look at the playlist lessons on properties of radiation and nuclear decay. That at least will give you a basic concept of how radiation works and get you used to the atomic notation that we'll use during the lesson. If you feel comfortable with it, you don't need to do that, and most of that material is separate from fission, but it may help you to check those lessons first, even if you've already seen them. All exercises will have their solutions linked at the top of the description. As always, I will indicate when you need to do an exercise and where you can find those solutions at the time. There's going to be a lot to do, so make sure you have your pen and paper on hand, and I would also suggest a pencil if you feel like doing some sketches. If you're working on a computer, make sure you have your screen cap tool to hand, because that will definitely save you a lot of faffing around. But without further ado, class is in session. Let's begin. To start us off today, I want to do a quick recap about atomic notation. This is something that we've discussed in previous videos and lessons before, but it is also something that comes up a lot in the nuclear topic overall, so it never hurts to have a reminder. So in those previous lessons, which you may or may not have seen, I introduced this notation for an atom, A, Z, X. You may or may not have seen that before, and you may or may not remember it, but in that little notation, you can learn an awful lot about the element you're working with and the isotope that you're working with. So what I'd like you to do, give yourselves 2 minutes to try and refresh your memory if you've seen it before. What does A, Z, and X represent? What do they stand for in atomic notation? Give yourselves about 2 minutes for that. And when you're happy, or if you've never seen it before, check the link in the description that is labeled as Starter Solutions. Once you've done that, we can move on and have a proper talk about nuclear fission. Because once we've done this, we're going to use this notation a lot throughout the lesson. So I want to make sure everyone's got it in their heads before we get started. So 2 minutes if you think you know it, and when you're ready, or if you've never seen it before, top link in the description labeled Starter Solutions. When you're happy, we'll move on and we'll talk about fission. So, nuclear fission. Nuclear fission is very, very important to a lot of things we do in society. Believe it or not, splitting the atom all the way back in 1944 or 5 with the Manhattan Project and everything that developed. A lot has come from nuclear fission. But how does it actually work? Well, nuclear fission is actually very simple. A large, what we call parent nucleus, splits apart, splits or breaks to form what we call daughter nuclei. I'm going to put 2+ here. Typically, it's 2. Normally you'll find 2 nuclei left over, but sometimes on the rarest of occasions you might find more, but typically it's 2. 2 plus daughter nuclei. I don't know how and why they gendered it. They just did. Thanks. Daughter nuclei plus some neutrons. That is essentially all nuclear fission is. It's a large nucleus breaking apart. So it might be that you'd start off with, I don't know, probably the most famous example of a nucleus that can do this is uranium-235. So if that is a nucleus of uranium-235, obviously there's a lot of protons and a lot of neutrons in there. You could write it in AZX if you wanted to. U-235 will split and go on to form some daughter nuclei, say 2, and some neutrons. Now, uranium-235 is very particular in that it releases 3 neutrons, which is why I've drawn it that way. And that is all it is. And realistically, that's nuclear fission in a nutshell. However, there are some extra points that I want to add. First one being that all products have kinetic energy, which I've written as E subscript K, which is the standard notation in the energy topic. So all products have kinetic energy. Even if the uranium nucleus is mostly sat there just chilling on its own, when it breaks and it goes, all of these products, the daughter nuclei and the neutrons, have got kinetic energy. They are going to move. Nothing is sort of left sitting there as a remnant. Everything goes. That is the first point. And the second point is how this happens. Fission can be one of 2 things. And these are 2 very important terms and 2 very important distinctions. So sometimes we have what we call spontaneous fission, or we can have what we call induced fission. So I'm just going to sneakily underline those. Spontaneous or induced. And if you know your English quite well, you might be able to interpret what that means. So in spontaneous fission, this is what we have. In spontaneous fission, the nucleus, the parent that is going to go, just goes. It fissions. There's not a good term for that. It fissions all on its own. Nothing has to happen, just at random, at some unknown point in time and space, it will go. It will fission all on its own. Spontaneous, off the cuff, randomly. At any random time, any random place, it can just go. However, most commonly, we focus on what is called induced fission, which I'm going to put as this sort of little green box to sort of note the difference. And in induced fission, what happens is a neutron comes in and what we call bombards the original parent nucleus, and then it goes. This all happens because of instability, because you need to have a large nucleus. And we talked about this in our alpha decay section back a few lessons ago. We talked about the idea that large nuclei struggle to hold themselves together because of the forces between them not being strong enough to overcome electrostatic repulsion. Well, in this case, it's even worse. It's so bad that they might just break on their own. And if you add another neutron into the mix, it's even worse. These fission neutrons bombard, so it's going to be another key word. So there's a bombardment by neutrons onto the fissile nucleus in order to make it fission. And that then creates this process, and you might have actually spotted what's about to happen. Because if you look at these neutrons, this is something we're going to talk about in a moment, these neutrons still exist. People sometimes think, okay, I've split the atom, I've broken it into two daughter nuclei, great. Oh, and there's also neutrons, who cares about those neutrons? This cares about those neutrons because we don't generally have one uranium nucleus sat there all on its own. No, we might have another one over here. And if that neutron runs into it, boom, this happens all over again. This nucleus now does what this nucleus, I will say it the English way, sorry Americans. This nucleus is going to do what this nucleus just did and pop. So fission can happen over and over and over, and this is where you get chain reactions, and this is where you get trouble. And we will talk about that in a moment. So I will put up a full comprehensive set of notes on the screen in a moment for you to take down. This is a shorthand and a diagram to help you, so I suggest you do draw this diagram, but a full set of notes is going to come up on the screen in a moment to help you take down the key points about nuclear fission. Once that's done, we're going to show you a very short nuclear fission equation, which is going to be very similar to the decay equations that we did in our alpha, beta, and gamma nuclear decay lesson a few weeks ago. So, to recap, draw this diagram and copy down, or in your own words, rewrite the notes that are going to appear on the screen in a moment. When that's done, you're happy, a question is going to appear about using AZX notation in a fission reaction. Have a go at that, and the solutions for it will be linked in the description under the subheading Decay Equation Solutions. So click that link when you've had a go at it, or if you've never seen decay equations before, click it when you get there and I'll walk you through the solution, because I understand not everyone has seen decay equations before from our prior lesson. So that's what you're going to do in a moment. Once that's done, we can move on and we're going to talk about this part, chain reactions. So now that we've got a basic idea of what fission is, how it goes off and what it does, let's have a talk about something I hinted at the end, chain reactions. So as we've mentioned, a fission reaction, usually at least, now not every nucleus can fission, in fact most don't, but when they do, usually you get a release of neutrons. You might remember that. If you remember, the 235 went on to create its daughter nuclei, and then 3 neutrons came out at the end. But remember the other thing. These neutrons can induce another fission. So you might remember induced fission happened when our neutron bumped into our U-235 and caused it to go. And that released 3 more neutrons. And when those 3 neutrons are just sent off, if they bump into another U-235, they're going to cause another fission. And spoiler alert, they are going to bump into another U-235. So this sort of thing will happen. So let's say we start off with 1 neutron. That neutron goes in and creates a reaction with a U-235. We've seen this happen, and we'll ignore the daughter nuclei for a second, but that then releases 3 more neutrons. And each of them, because of the sheer density of uranium, is going to hit another uranium nucleus. Do you see the problem? So this is called a chain reaction because each of these is going to release 3 more neutrons. Do we see the problem yet? Because each of these neutrons is going to bang into another uranium nucleus and release 3 more neutrons. Do we see the problem yet? This is a chain reaction. The reaction, a chain reaction, and yes, I can probably hear you singing that song from the other side of the internet. I know the joke. A chain reaction will continue on its own. So once you get that chain going, if you think about like a line of dominoes, you knock over the first domino and it hits 3. And each of those 3 hits 3 more. And each of those 3 hits 3 more. So you've got 1, 3, 9, 27, 81, 243, 729. And now I'm just showing off my 3 times, powers of 3. Yeah, this goes very off very fast. And when it goes, this happens. I don't think I need to tell you what one of those is, and no, it's not a tree. This is the principle behind the atom bomb. Straight up. An uncontrolled chain reaction will release so much energy that you get an atom bomb. Yeah, that's how important and how dangerous nuclear chain reactions are. But there is a caveat. This is terrifying, and we don't ever want to do this again. Ever. Please. Goodness no. No more of this. So what we do is we do something called control rods in our nuclear reactors. We're going to talk about reactors in a moment. And that is going to show you sort of why we can do nuclear fission of uranium-235, which does this and will end up with this, and yet we can do it safely. And we'll show you what that means and create what we call a steady state reaction, where instead of it being 3 neutrons at a time, we're only releasing or only colliding 1 neutron with a uranium, not 3. So the reaction doesn't go out of control. And that's a really important distinction. So chain reactions, in short, fission reaction releases neutrons, normally anyway. And these neutrons induce another fission, leading to a chain reaction, which is this. And this, if left unchecked, which I'll just sort of put in a bracket, if left unchecked, is a problem. In fact, I'll make it doubly clear that I haven't drawn a tree. I don't know why I'm so good at drawing this symbol by eye, but there we go. If a chain reaction goes uncontrolled and unchecked, boom. And the chain reaction will continue on its own. We have to control it. And that's what we're going to talk about in a moment with nuclear reactors. So, copy this down and draw the diagram. You might not want to do quite such a dramatic drawing as I have there. I've sort of done that for effect. But sort of make it clear that if a chain reaction goes out of control, big problem. Therefore, we must control it. And that's what we're going to talk about in a moment. So now that we've had a look at what a chain reaction can do, we need to understand how we harness that power in our nuclear fission reactors without any of the dramatic consequences I already mentioned. And for that, we've got a lot of moving parts, literally. So a fission reactor is actually very similar to a conventional reactor. So, for example, a coal reactor, a fossil fuel reactor, that's the term we'll go with. Fossil fuel power station. Because they actually use the same method to generate electricity. Steam drives a turbine, leading to electricity. There's a bit more to it than that. You'll have probably done it in your energy topic if you're a bit further on in your GCSE. If not, you will meet it at some point when it comes to power generation. But the basic principle is the same. But using fission of uranium, it's usually uranium. You may also find plutonium, but very often you will find uranium instead of burning fuel. Like I say, it's a very similar concept as a power station. In fact, you only have to swap out the furnace or wherever else you're burning the fuel for a fission reactor. But there's a lot going on in that reactor. So I'm not going to get it all on here, so I'm probably going to need 2 segments to get all this down. So make sure to copy down this segment first, and then we'll do the second one as well. So inside the reactor core, it's the first keyword, or first key component. So the reactor core is sort of the shell, the container inside which the fission reactions happen. Fuel rods. We use rods to try and maximize the amount of fission we can have at any one time rather than one big lump of uranium. They're thin rods and we have loads and loads of them. Are surrounded by what we call, well, they're surrounded by water as a coolant and a moderator. So I'll define a few of these terms in a moment. But this is referring to what we call conventional reactors in the UK and across a lot of Europe. These are the very European reactors. Some reactors in Britain still use the old method where they have a gas moderator and a separate coolant. They're done very differently. These carbon dioxide, no, graphite-based nuclear reactors. But we don't need to talk about those for this course. We talk about the ones that use water as their co-coolant and moderator to sort out the neutrons and stop things from overheating and going kaboom. The other thing that we have, which is most important perhaps of all, is something called control rods. Now, these are made typically of boron. You don't need to really know why for this course, although it is a very interesting bit of theory that I did as part of my degree. Control rods absorb most neutrons to prevent how's the best way of putting this? I think the best term we use for a reactor is a meltdown or going critical. So if a reactor goes critical and has a meltdown, well, you get Chernobyl and things like that. Generally, they're not as bad as Chernobyl. Chernobyl is a catalogue of catastrophes. I might tell that story one day. But it's basically there to prevent the chain reaction from going out of control. It creates what we call a steady state reaction. And you will get a chance to draw and label up a diagram of this in a few minutes. But last off, let's just define this steady state reaction thing, because we're going to have to take a few bits down and then move on to a second page. So, as you saw earlier with our uranium-235 fission, it creates 3 neutrons. When you start the reaction, you have 1 hits a uranium, 3 neutrons come out, they all hit a uranium, 3, 3, and 3 come out, that's 9, and so on and so forth, big bad trouble. What the control rods do is they are dropped in between the fuel rods. mostly, not all the way, but mostly in between the fuel rods. And what that does is it absorbs about 2/3 of the neutrons. In an ideal world, you want to have one neutron for each fission to go on and have another fission. So, have I got a way of doing this? So, yes, I should have got my bouncy balls out. If I have my 3 neutrons that came out from fission, my control rods are going to block, say, these 2 and absorb them. So these 2 now can't do anything. They've been absorbed by the control rod, leaving just this one to go on, hit a uranium, and cause another fission reaction, which will then release another 3, and will block 2 of them, leaving 1 to create another fission, and so on and so forth ad infinitum. What that does is it keeps the fission reaction ticking over and never stops the reaction, so we're constantly generating energy, generating electricity. You don't create energy. Generating electricity, but not to the level where the reaction goes out of control and we have a problem where the reactor goes critical, has a meltdown, or otherwise blows up. And we don't want that. But the other thing about the control rods is that they can move. So you'll often find the control rods sort of stick out of the top of the reactor whilst the fuel rods are fully inside the core. And these rods can be lifted in and out and in and out and in and out. And that means if we lift them up, we get more fission. So the reactions go faster and we generate more electricity than we would as if we dropped them in. If we lowered them all the way down, we can stop the fission dead and stop the reactor from doing anything, which is very useful if we have a mechanical or technical fault. And that's where Chernobyl went wrong. Oh, like I say, I'll tell that story another time. It was a major mess of control rod mechanisms and incompetency. There's a TV series I think that was done on it, if you can find it on the Tinterweb, although I'm told it is rather graphic in some places. Anyway, so there's your first set of notes on nuclear fission reactors, talking about what they are, essentially, in terms of the power station, in that they're very similar, and some of the first components, and you will get to draw this in a minute. So you've got the reactor core containing fuel rods in it, and control rods sort of laced in between, sticking out. Around all of that is your water, which is both a coolant and a moderator. What that means, I'll talk about in a moment. And then from there, a lot of it is very similar to a conventional reactor. You boil up some water, and that generates steam, goes off to a turbine, drives the dynamo, diddly-diddly-dee, out comes electricity, everybody's happy. So, take that down, and we'll talk about the other bits in a moment. We've already mentioned about control rods, what they're made of, how they work, but the other key terms that come up in terms of labeling a reactor and describing its functions would be that of a moderator, a heat exchanger, and the fuel rods. Two of those terms we've already seen, but we need to explain what they are. So the first one that should be most obvious is the fuel rods. Contains U or Pu, where Pu is plutonium and U is uranium, and is where the fission happens. One quote I use to some of my old students is, it's where the magic happens. However, it's not magic, it's just science, so don't quote me on that, it's just a turn of phrase. Where the fission happens, and I'm going to put in brackets, gets hot. Very, very hot. These things get very, very hot because they release so much energy from a single nuclear fission that it's kind of crazy, which is why we need that coolant to stop it from getting too hot and melting the fuel rods. That's the way that meltdown comes from. Is another part of why we have the control rods, is to stop too much fission happening, and the coolant is there to stop it going out of control so that it stays cool and doesn't melt, because then we have problems. Now the moderator, its job is to slow down neutrons. It moderates their kinetic energy. That's where the term comes from. Slows down released neutrons to make fission, or to make future fissions, more likely. Now, this might not make much sense without a bit of a deeper understanding on nuclear physics that you don't need, but essentially, a fast-going neutron is more than likely going to just whiz past a uranium atom or bump into it and displace something, whereas we want, in the fission reaction, the uranium or the plutonium to capture, if you like, the neutron and therefore have the fission happen. So we want it to catch it, so we want it to be moving slower. So we slow it down, we moderate it, we thermalize it, if you want to get into the full fancy term, and it means that they're more likely to cause a fission. And this is usually done as water, or in some of the older reactors that I made, or some of the reactors in other areas of the world, they sometimes use graphite. This is what a lot of old British reactors used to do, is they had a graphite moderator and a carbon dioxide, was it carbon dioxide coolant? Yeah, carbon dioxide coolant. It was a solid gas reactor rather than a liquid reactor where we have the water doing the moderator and the coolant job. So it sort of varies where you are in the world as to what your moderator and coolant will be. The last piece is the heat exchanger. So what this does is actually in the name, boils fresh water using heat from moderator / coolant water. You might ask, Tactica, why do I need to boil some water when I already have some hot water? Well, you'll see in a diagram that's coming up on the screen in a minute or two exactly what I mean by this. But the water around the reactor core is literally touching nuclear material where nuclear fission is going on. That water is being bombarded with radiation all the time. It is very heavily irradiated. It is not radioactive, but it is irradiated because it contains and has been given radiation that is harmful and dangerous by the fuel rods. And that's bad. We don't want that water going anywhere. So what we do is we pump it in a closed loop from the reactor core into the heat exchanger, around and around and around and around and around and around. So it goes into the heat exchanger, cools down by transferring its energy, and then goes back into the reactor core to act as a moderator and coolant all over again. Inside the heat exchanger is another set of pipes. Well, one big pipe really, that comes in and out again from the reactor. You pump water into that pipe, and that water has never seen any radiation in its life. It's fresh as a daisy. So it comes in, it gets hot, it boils into steam, and that steam goes racing off into the rest of the power station to drive the turbine and the dynamo and diddly-diddly-dee. That means that there's no radioactive steam or irradiated, radiation-laced steam being pumped through your entire power station, which is really dangerous if you get a gas leak. Instead, you've just got all your radiation contained very nicely inside the reactor core and the heat exchanger on one closed loop. And that is all contained again. All this core HE, which I'm just going to call the heat exchanger, etc., is encased in a concrete shield. Those who have seen my previous lessons on properties of radiation may know why already. This is to prevent any excess radiation that can get out of the core from going anywhere. So the reactor core is usually made of steel. It's a pretty dense, thick block of steel, but it's steel. And as we've seen in previous lessons, if you've seen those, not all radiation is created equal. Some of it can get out. If it's got very high energy, particularly, it can get out. So if it gets out of the reactor core, where's it going to go? Well, if your reactor core is exposed, it's just going to whiz off into the air, and then you're going to have all sorts of radiation leaks. So what they do is they box it up in this big concrete shield, because concrete absorbs basically everything, and that prevents the radiation from escaping at anything other than minute background levels that barely affect us at all and wouldn't really affect the workers in the power plant either, because it's all trapped behind that shield. You go into that shield, you're going to have more problems. But if you're behind that concrete shield, which is wrapping up your entire reactor core, it's not as bad. Right, I've talked and written a lot. So what I'm going to do now is put on screen a partly labelled diagram of a reactor core and the wider system. So you've got the core, the heat exchanger, and the whole system of a nuclear fission reactor at work. And what I'd like you to do is label each of the components of the reactor using the descriptions that you've written down and that I've talked about. So you might need to listen back to this segment, and I know it's like 15 minutes. You want to listen back through this segment so you can label it up. I've tried to give you sort of a schematic image in your head, and this will be your chance to actually see one, not in action, but see one in schematic form and label it up. The solutions to that exercise can be found in the description under the name Diagram Labeling Solutions. So that's the third link down in the description. So when you've had a go, give yourself about 8 minutes, click that third link in the description to check the solutions and see how you got on, and then annotate it when you're ready. And with that, we pretty much are at the end of the lesson. So we're going to have one last little mini activity to wrap up the lesson, but in terms of the teaching material, we're good. Diagram's going to come on screen, 8 minutes, label it up, good luck. And now we are at the end of the lesson. You've had plenty of time to take notes, answer some questions, and I'm sure you'll have had plenty you want to ask as well, in which case the comment section is right down there. But we're going to do a quick little summary question that I'd like you to try and answer. I'm confident you'll get at least most of it, so let's see how we do. It's a two-part question. So part A is, when a parent nucleus fissions, that has an S, what are the two types of products? Of course, there are more than two products because you'll often see several different things released if you remember back earlier, but they generally come into two types or groups of product. So what are the two types of product from nuclear fission that we've talked about today? And part B, what are the risks or hazards associated with them, with these products, when it comes to a nuclear reactor? Now, one risk I think you'll get very quickly because we've talked about it today. But the other one is one that I've mentioned but might be a little bit less obvious to pick up on. In fact, in some ways it's more obvious, but it's also less obvious. So give yourself about 4 minutes to have a go at this. Pause the video and answer the question. You've got about 4 minutes. Best of luck. Off you go. And now that you had a chance to pause the video, we're going to go over the solutions. So, when the parent nucleus fissions, the two types of products are the daughter nuclei. Again, still don't know why they gendered it. The daughter nuclei, so the two or more nuclei left over. So if you remember back to the earlier question, we had that uranium nucleus that fissioned, and it created two nuclei. I think it was krypton and barium, as I remember. And the second type of product was the neutrons. And we've talked a lot about the effect of those neutrons throughout the lesson when it comes to things like chain reactions, control rods. There's plenty going on there. So the risks or the hazards, well, there's actually one each. On a sort of baseline level. And for a start, we'll go with the neutrons because I think this is the one you'll have picked up. The neutrons can cause a chain. Neutrons do cause, not can cause, do cause a chain reaction. Now that is the hazard, or that's the risk, and the hazard of that is that the reaction can go out of control and we get a meltdown and the reactor goes critical and kaboom. That's a problem. That's the hazard associated with this risk, or the other way around, you could say. Always get those two terms mixed up. You shouldn't. But in terms of mitigating that, you should know how we deal with this, and that's through the use of control rods, which will absorb the neutrons in those big boron rods that you have labelled on your diagram. The second point comes from these daughter nuclei. And they are very often, if not always, radioactive. Usually radioactive, which means that they are going to give off and emit different types of radiation, alpha, beta, or gamma. Heck, they might even fission again. It's very unlikely, but they might, if they were heavy enough, fission again. And that is a huge problem because that's just a giant pile of radiation being pumped out of our reactor and out of our fuel rods. And so we need to defend against that because otherwise we've got all sorts of problems and the risks of radiation are well known when it comes to affecting the human body. And so to mitigate that, you might remember we have the reactor core, which is that big steel container to absorb some of the radiation. We also have the concrete shield around our reactor, the whole system, in order to prevent gamma radiation from escaping. And you'll also remember, hopefully, that we had the heat exchanger so that the water being pumped into the power station was kept entirely separate from the water being pumped around the reactor. The water in the reactor was being used to heat the water that went to the power station, but no irradiated water was ever leaving the system. So we have several things we do to mitigate against the radiation and the irradiation of the water. So there's plenty in there in terms of hazard management, and they're all things you might want to consider if you get asked a big long question about nuclear reactor design. And with that, we are at the end of the lesson. That is everything I think you need to know about nuclear fission. We've explored what it is, how it happens, what you get out of it, what the problem with that is, and we've also then explored chain reactions and the design of nuclear fission reactors and how they are set up to allow nuclear fission to happen and generate electricity from them, but also how we mitigate those risks and make sure that the fission is safe to prevent creating another Chernobyl. There's plenty there. And if you would like me to do a bonus based on history, talking about the history of Chernobyl, Fukushima, and maybe some other stuff. I did study at university some advanced nuclear physics, and a lot of that involved reactors. So I'd be more than willing to tell that as a little history lesson sometime. Maybe as a little Tactica Tutorialis addendum if you feel like learning some history on top of your science. But let me know in the comments on that one. So, thank you very much for all of your hard work, your time and effort, and for creating the sets of notes that I've asked you to do. It really is pleasing to see people have a go at the exercises and check the solutions. I do see them get views, so it is appreciated. If you have any suggestions for future lessons, any requests, please do let me know. I'm thinking of doing another couple of lessons on waves. I want to do a lesson on the life cycle of a star, and I'd also like to obviously wrap up from fission by doing about nuclear fusion. So I've got several lesson ideas I want to do before the end of quarantine and people going back to schools, but let me know in the comments if you have any particular requests. I always try to honour them. But with that, class dismissed. Thank you very much for watching Tactica Imperialis, and this has been my Tactica Tutorialis lesson on nuclear fission. I nearly got that wrong. I'll see you all again. Bye for now.